Now today I will focus exclusively on wind energy. Uh, now, the benefits of wind power. One is, of course, I think maybe I should put it down. Maybe it doesn't really tell the whole story. Okay? We'll put self-reliance, reduced dependence on import. Right? You'll agree, no? That's very important. Okay. In fact, we should put it right on top of you.
Yes, sir.
Yeah, it's so important, And and then of course, environmental benefit because you're not using any fossil fuel. Okay, there are no emissions from a wind mill. Okay, you don't require fuel. Okay, the other is because wind energy is fairly distributed, although in India, that's not really the picture. Like the western part of India and the southern parts have uh, some potential, reasonable potential for wind energy, but the eastern part of the country doesn't have that potential. So, in fact, it's not a bad idea that if you have to use coal, at least for some time, and the eastern part of the country is what has coal. So maybe the coal-based power generation can be in the eastern part, and one could focus more on the western part for renewable energy because both solar and wind tend to be better, in the western part. Okay, so those are the things to remember. Now, another very important thing about wind energy is that it's quite a silent form of energy. In that sense, it is quite similar to solar photovoltaic. I mean, just imagine, you just have got those panels, they don't make any noise, nothing, and they're generating power. Likewise, of course, even here, although the rotation of the windmills does generate some noise, but it's not very substantial. But there is one concern. I'll just put uh, general perception that windmills have driven away the birds. You know, in fact, it's interesting that I don't know whether really it is true or not, but this perception exists. That birds get scared when they see windmills. Maybe because they get scared for that reason. But actually, a windmill is not like a fan. It's not as if I've turned on a power and the pankha has started rotating. It is the wind, the natural wind, which is making the turbine rotate. It's the other way around. Okay, it should not have made much of a difference. Okay, but that perception definitely exists that it is harmful for birds. So just keep that in mind. Okay. Now, what causes wind? How is wind formed?
Sir, development of high pressure and low pressure.
Wonderful, wonderful. And how does the development of high pressure and low pressure happen?
Sir, because of temperature mostly.
Wonderful, very nice. Okay, excellent. Student, high pressure and low pressure regions, and due to because of temperature. Due to temperature. Very good. Very good. Okay, and in fact, you have already answered the question, but let us go through it. Uh, what is very important to note, is that it is all because of the sun, the energy of the sun. All right. So in a way, wind is only a manifestation of solar energy. It's just in another avatar. That's all. Okay. And so what is the sun really doing? I mean, it's creating this differential pressure. So for example, because of the higher I mean during the day, the land heats up. Okay. And so the air above the land becomes less dense because of the expansion of the air. Okay. And comparatively, the temperature difference in the sea is not much, because in the sea, you don't have this kind of a situation. There's also a cooling effect which is provided by the sea. Okay. And so what happens is that this is the region of high pressure during the day, and this is the region of low pressure. So the direction of wind is from the sea to the land, as all of you know. That's the sea breeze. And in the night, the land cools down faster than the whatever happens in the sea. And so again, the air becomes heavier, in the land now, exactly the opposite of during the day. And so now the pressure gradient has got reversed, and this is the higher pressure region. And so wind flows or is formed by the movement of air from the land to the sea, and you get a land breeze. Okay. And so it's all about really heat which is being provided by the solar radiation that is falling on earth, and because of the uneven effects that take place in different locations, like the land and the sea. Okay. And that anytime there is a pressure or there is a gradient pressure difference, there will naturally be a gradient that is created. And the now over here, obviously the heat balancing is not being done by radiative mechanism. I could have said that can it just radiate heat from the land to the sea. Okay. This is all because of convective redistribution of heat. Okay. So air will flow. Okay. It's mobile. Air is it can flow, and so obviously the preferred pathway will be really the convective process, through which this temperature redistribution will happen, and that's what causes motion. Okay. Now, in addition, there is one more thing that you need to note, which is that as we have discussed when we are talking about solar energy, that our Earth is also rotating. Okay? And is rotating in the counterclockwise direction, as you can see. So obviously there will be the wind will have a curvature. It will not necessarily be going in linear, okay, direction. It will get curved because of the rotation of the Earth. Now, if it curves in the same direction as the rotation of the Earth, then we call it cyclonic. Okay. So if the wind move to the right, in the northern hemisphere, we would say that it is cyclonic. However, there are situations where you could also have the wind going in the reverse direction, you know, to the direction of rotation. And if that happens, then it will be called anticyclonic. Okay, and in the southern hemisphere, the behavior in terms of clockwise and counterclockwise would be opposite with respect to the people who are here, how you will see it. Now, and as I told you, I mean, it is really the redistribution of thermal energy that is happening in the course of the flowing of wind. Okay, so obviously it happens with a clear sense of purpose. Okay. Now, it's also very important to just check with you. Do you think that wind velocity depends on the height above the ground? Does it vary with height, wind speed?
Yes, sir.
Yeah, it does. Okay. And so what happens is that, on the ground, there are, of course, always there will be objects, right, near the ground. Okay? And there could be buildings, there could be hillocks, things like that. I mean, there could be so many things, or even buses and cars moving in the on the road. So what happens is that obviously when the wind is going and hitting these, there will be a friction, and so some of the energy will get dissipated because of these kinds of frictional forces, between the wind and these objects, which are, whereas, if I go above, I don't have any objects which can retard the flow of the wind. Okay, so there's no really frictional force there, and because of the frictional force, naturally, I mean, there will be a this kind of a slowing down, obviously, because some of the momentum has got transferred, and so there will be a reduction of velocity, and so there can be also a gradient that is created from top to bottom. Okay, because of that, right? So you can see that it can be quite complex. One is, of course, the heating up effects, which will cause differences in pressure and wind and things like that. And then you have got these other factors plus the rotation. So in a way, it's quite complex to if you really want to study it in depth. Okay, then obviously this itself is a branch of engineering, and you could devote your entire research career and your studies to entirely this, and not just one person. There are hundreds of people who are working on this. Okay. Now, so there's another factor which is important to note, that when we say high and low pressure regions, as you all have mentioned so correctly, okay, it also depends on how close together are these high and low pressure regions. Okay, like if they're very far away, then there will be only a mild pressure gradient. Okay, now typically, I don't know if you, whenever you see on television and they'll show there's a cyclone coming or whatever, and you see things swirling around. Okay, and so wind has very complex patterns. Now typically what happens is that within a zone, you don't have a uniform distribution of wind. What you have are isobaric regions, so this would be like one zone of a certain pressure, this would be another, and you can see that the pressure here is more. Okay, it's less, and it's got still less here. Okay, so that's what, so obviously the the thrust is being provided by the wind at the highest or the air which is at the highest pressure. Now take the low pressure zone again. Again, there would be these kinds of isobars, right? Uh, Regions of constant pressure. Okay? And this would be the lowest, and these would be the it gets increase higher in this particular region. Now, what happens is that the air now obviously starts flowing from the high pressure region to the low pressure region, and this is, you can see the direction of flow, and what it will do is that finally it will find its way over here, because this is the lowest pressure region. Okay, so and it will do that in this kind of a very cyclic rotational movement, almost like spiraling down, okay, to the center. Okay, and again, I mean, obviously these are also heavily influenced by the rotation of the earth, and so this is what you normally will see, when people are showing you weather patterns, and these patterns are so complex that you cannot in a simple way really analyze and say this is what will happen. In fact, weather forecasting and forecasting of these kinds of turbulence and cyclonic storm, etc. All of these, I think the biggest use of supercomputers is really in this area, of monitoring of these kinds of weather events. Okay, so quite a complex thing. I mean, this is only a qualitative, simplistic way of looking at it, but that, of course, is not what climatologists do. They will, meteorologists, they will of course be able to do it in a much more quantitative way. But for your course, for this course, I think this is sufficient as information. Is that clear to everyone? Everyone is
Yes.
clear? Okay. Okay. Now, so we also talked about, that these obstacles, etc., and that they can retard the flow, and there are frictional forces, but there are also some other effects which are interesting to note, like for example, like hilltops are typically they will have a convex shape, right? I mean, hills are typically well, not all hills, but there are many hills, the top looks like a convex shape. Now, what happens is that when air flows, like let's say it's flowing with a, velocity of v1, and because of several effects, one is that obviously, the air here, it will just go and hit against the hill at the bottom. So it kind of all of this air will naturally go and find their way to the top of the surface. Okay, and that's how they will move. And so what happens is that the lines of force, get concentrated in the top of the hill. Okay, and the more the lines of force means that the more higher will be the velocity, okay, of the wind. And in fact, you'll find, in fact, I've seen many places where you'll find that windmills have been set up on small hillocks, and that's the reason. Okay, because finally a windmill will work effectively when the more is the wind speed. Okay, so obviously, you'll try and maximize it, and you've got to maximize it by the natural topography of the land. You cannot do anything in terms of artificial intervention. It's not practical. So these are the kinds of things that people have studied and why, for example, the windmills are many times placed on the hilltops, even though obviously there's a lot of hassle in maintaining these windmills because they're on top of the hill, but even so, the gains are so much that people put them up over there. Okay, and there are, of course, many other types of obstacles as we talked about. Buildings, this, that. So some of them can be beneficial, like in this particular case, and some of those could, of course, retard the flow of your wind or slow down your wind. Okay. Now, let us quickly see. The wind velocity is higher the higher up you go. Okay, when you are, let's say, if you are planning to set up a windmill, you must know not only what is the which is the best location to try and put the windmill in our country or in our state, whichever state you want to set it up in. Is it worthwhile setting it up? And then obviously look for uneven contours, and where if there are hills and things like that, see if you can locate it there. If they're also closer to the sea coast, and you have this advantage of the land and sea breezes, that's great. And in fact, like in Gujarat, if you go, I mean, when you're going from Porbandar to Dwarka, there are thousands and thousands of these windmills. I mean, even in Maharashtra, the other day I was coming from Latur, and we saw so many of them, but nothing like what you see in Gujarat or in Tamil Nadu. The numbers are staggering. The number of windmills which have been set up. Okay. Now, so there is a way. So you suppose I want to set up the windmill, and I also want to find out that at what height. You have seen that all these windmills are very tall, right? They've got a uh, tower, and then the turbines are basically fixed on the hub at the tower. And so you need to know all these things, that what should be the height of the tower, what should be the length of the blades, what should be the shape of the blades. There's n number of things to look at. Now, this is a formula which will quickly help you to figure out the wind speed at a particular height. Okay, and it's very important to actually do that, because you'll find out later on that the energy, the power that you can harvest from the wind is not linear with V, and so there is a huge implication of wind speed. Okay, so it's not a small thing if I see only small changes in wind speed. So this formula has been worked out. Okay, where what you have is, like, suppose I want to measure the wind speed at a height z. Okay, so this is what my unknown is. This is what I want to measure. Okay, and I of course know the height at what I want to which I want to measure. Okay, now to do this measurement, what you require though is that you need to know the wind speed at some reference height. Some height. I mean, you might take your anemometer there, or this data might already exist. That at a particular height, what is the wind speed? So if you know that is VR, so the reference height. So at a reference height, I know the wind speed and I know the height. Okay, and this Z0 is another very interesting thing. It's related to what we talked about, which is that it is a measure of the roughness of the terrain. where you are trying to set up your windmill. And I'll go through this. Okay. And, this whole area of basically understanding the contour of the terrain, etc., is known by the general term orography. Okay. So there are people who are experts in this area of orography. Okay, and it's a broader. It falls under the general broader area of what is known as geomorphology. And so this is something that geologists, for example, are and geographers, are very good at. Okay, physical geographers. So, what is meant by roughness? And it's actually a logarithmic profile. So, it's not as if it's linear. Okay, but after a lot of work, people have found out that roughness length, what is known as Z0, okay, has very very different values for different places. Like for example, if I go and put up a windmill in the sea, okay, and there are, in Europe, okay, there are so many of these windmills you'll see in the North Sea. I mean, the North Sea is probably the most productive place for generating wind energy. Okay, now, this roughness factor is very low, in these kinds of areas, like in a river or in the sea. Okay, 0.0002. You can see very very low. Okay, and it is measured in meter. This roughness length. Okay? Now, then you could have areas which have it's like farmland, because in any case you set up windmills in areas which are relatively less congested, right? Also because it requires a fair amount of land, and you can't get the land in the heart of the city. And so it's quite common to put it up a bit further away. Okay, so like farmland could be an area, or hilltop could be another area. Now, this water would have what is known as a roughness classification of 0. Okay, and a farmland with very few buildings, some trees, but not too many. Okay, or like airports, which are mostly empty spaces, but then again, there is of course some building and things like that in an airport. Those kinds of places will have a value of around 0.03. Okay. Now, farmland with closed appearance. When they say closed appearance, means there are generally more constructions. Or if you take our airport in Mumbai, I mean, okay, the airport area is obviously quite empty, but I mean, it's surrounded by all buildings and this, so it would have a closed appearance. That kind of place. That's what is meant by closed appearance. That would have a roughness factor of 0.1. Okay, and then of course, suburbs means these are typically a lot of this information gets generated in the US and all, and their suburbs are quite different from our suburbs. It's not like Kalyan and Dombivli. Okay, and it is different. Okay? And so our suburbs would be very, very much more congested with buildings, and I think that our roughness factor would be much higher, over here. But in their suburbs, they have a roughness factor of 0.4. So let us quickly do a calculation, okay, of how, for example, the wind speed is measured in a particular at a particular height. Okay, so this is the example considering a wind blowing at a reference height. The reference height is 20 meter and the wind speed is 8 meter per second. Okay, and then what they want to do is that they want to find out that what would be the wind speed at the hub of the windmill, which is located at let's say a height of 50 meter, okay, from the ground. So this is the hub of the windmill, 50-meter height. Okay, and it's also giving you the information that is describing the type of terrain, okay, and for which they have basically, based on all the their understanding of this location, they have decided that it falls into this category, Z0 equal to 0.1. It means roughness class of 2. Okay, so they have given it a roughness class of 2. That's what they've done. Okay? So we at the wind speed at the height you want the information at 50 meter is equal to the wind speed at the reference height of 20 meter, which is 8 meter per second, and then log of z by z0. So z is 50 meter. So 50 divided by z0 is 0.1. Okay? And that whole thing divided by ln of z reference. Okay, and z reference was 20 meter, so that's 20, and your same divided by roughness factor of z0, which is 0.1. So that's what you have, and you can work it out, and you'll get a value of 9.38 meter per second. Okay? So you can see that at the height of 50 meter, the wind speed is gone up. Okay. Now the question is that how high should I go? Of course, it's gone up means it's an advantage. I'll be able to get more wind power. Okay, but the point is, it also adds to the cost of making a windmill. So what people have done is that they have created this profile, okay, which is the relationship between height, okay, and the wind speed. Okay. So what you can see, it's quite interesting that of course with at the higher height the wind speed is going up. Like for example, if you're at a height of something like or if you're at a height of say maybe about 25 meter, you can see that the wind speed is very low. Okay, not very low. Over here, at least what they've said is it's about 8 meter per second. Okay, but moment I go to 50, then it's become higher. That's great. But then it's a diminishing return. So that even if I go to 300 meter, my wind speed is not really going up to anything more than 12 meter per second. So obviously, people will then say, look, I don't want to go into that much of a height just for these marginal gains. So let me put up the windmill maybe around here, 100 meter or 100 or thereabouts. So, I mean, that's for, of course, people to decide that how high they should go up. Is that clear, this plot, to everyone? All clear?
Yes, sir.
Okay. Okay. Now this is also very interesting that if you look at that wind has been classified into 7 classes of power. Okay, which are 1, 2, 3, 4, 5, 6, 7, as you can see, and of course this also depends on the height. So For example, at 10 meter, 33 feet height, you can see the wind speed, and at a height of 50 meter, what is the wind speed. Now, and by the way, I mean, some people might give you wind speed in miles per hour, or it could be kilometer per hour, or it could be meter per second. So you must be able to convert one from the other, and there is a 5 by 18 factor which all of you are aware of, from meter per second to uh, uh, this, and so you can quickly work it out. Okay, and so now what you see is that if I am at a wind class, power class 1, okay, where the wind speed is about 4.4, okay, at 10 meters, I will get a wind power density is what? It is just the wind energy per unit time. Okay? Any power is per unit time and per unit area. Okay, the area on which it is going and hitting. So that hitting was occurred with what kind of a power, per meter squared. Okay, and power is of course got the unit of watt, joules per second. Okay, so that's watt per meter squared. Okay, and so you can see that, for example, in solar energy we talked about uh, power densities of around maximum peak power densities of about 1 kilowatt per meter squared. Here, you can go to things even up to, it can vary by quite a bit, and in fact, it can be even higher. It can go to even 5, 600 watt per meter squared, or even higher in some cases. Okay, so you can see now what you'll see is that when you are looking uh, at something like this, okay. Uh, so if you're looking at, let's say, a range, because wind speed is never going to be constant. So the best thing to do is to give the range of wind speed, okay, which you'll get, because that could be more practical. Otherwise, somebody would you might get disappointed. Someone is, it's like no different from giving peak solar radiation and giving the radiation from 9 o'clock in the morning till 4 o'clock in the afternoon. Okay, it's not the same. So similarly here it's not the same. So best thing is that you give the range. Okay, and so you can see that in going from 4.4 to 5.1, it doesn't seem like a big change in the wind speed. Okay, but the at 5.1, this figure power density can be 150, so much higher, than this. It's about 1.5 times more. Okay, and over here at the higher height, you can see that the power density can be something like 200 to 300 watt per meter squared. Okay, so and you can go up to things like 800 watt per meter squared. Once you are here, or thereabouts, it's like peak solar insolation we are talking about. Is interesting, so these high wind speeds translate into wind power density which is quite comparable to solar peak solar radiation, which is 1 watt per 1 kilowatt per meter squared, and I hope you can see it's quite interesting that things turn out to be quite analogous in some ways. Now let us look at you know let us look at a world map, all right, and try and see what are the typical kinds of uh, 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 wind velocities, wind speeds that you have in different places. Okay, and so what you can see is that These are the wind speeds over water, okay, over here. Huh. And you can see that when it's getting very light, it means that the wind speed is more, okay. And this is over land, okay. And you can see that when it is more brownish, okay, deep brown, that the wind speed is more, and bluish is less. So in the water, you can actually see places, where, for example, where you might want to set up windmills. I mean, places like this, which are very, very light. Okay, or look at this. So that's why there's a lot of interest also in setting up wind farms in the water. Like as I mentioned to you, in some of the places, it's quite prevalent. Now, if you look at over land, yeah, we have very few windmills which have been set up in the water. We have, of course, there are complexities. It's not so easy to make the kind of civil engineering structures that you need to support such windmills. I mean, in the sea. Okay, but well, I mean, if there was a if energy shortage is such that you need to do it, then you'll do it. Okay, so I think that that's very, very important. That we look at that. Now, in fact, you can see, for example, in the Indian Ocean, if you look at these kinds of places, quite interesting. So maybe there is a strategic importance of trying to get some kind of a control on places like this. Okay. Okay. In the land, as I said, if you look at some places, like for example, look at Greenland, okay, or you look at South America, the tip of South America, Chile and Argentina, they've got very, very strong winds, going up to 9 meters per second. Now, what do you see in India? Okay, this is India. Okay, and you can see that our wind speeds are relatively low. Okay, it's only along the the west coast coastal area that you see that it is yellowish, over here. Okay, so so this is the place. Okay, and of course in Gujarat, over here, where you will also set up some of uh, these types of plants. Okay, so that's the reason. But you look at the eastern part, for example. I mean, it's very low, so it wouldn't make much sense. A lot of people might want to set it up, but it may not make much sense to really install windmills over here. Okay? And later on, you'll come to know even more the reason why that is so. Because you're talking about wind speeds of what, 3 meter per second, 4 meter per second, things like that. So it wouldn't make much sense to set it up here. Uh, Now, look at our neighbor China, for example. They are very lucky. Okay? Uh, their wind speeds are very high on land. Okay? Look, and the extensive range over which they have got this kind of high wind speed. So they're quite fortunate in some ways. Okay, so so they will be able to obviously generate much more of wind power than we will be able to. because of this. Yeah. Is this clear? Is the map and wind speeds and all clear? Did you understand?
Yes, sir.
Okay. Okay. Now let us look at the scenario in India. And I've tried to get some of the latest data that we have and total. Now if you look at this is for all renewables, we have talked about we've got about something like 97 gigawatt of installed capacity for renewables, which is broken up here. Wind power is around 40, solar power is slightly edged up, 41. Biopower is relatively low, okay, and hydropower is not that much, okay. Uh, I mean, there are of course some big dams, but by and large, it doesn't really. These ones at least don't contribute so significantly. Okay? Um, Now, in fact, the situation has changed quite dramatically. Uh, if one looked at the data, like even 15 years ago, or why 15, even 10 years ago, okay, this was extremely small, this value. Okay? And this was still quite substantial. And so what we had was that if you looked at our renewable energy portfolio at that time, what you would have seen is that wind power was dominating, you know. But because what has happened is that, we have more or less taken up all the area, wherever there was an opportunity to set up windmills with reasonable power density, we have actually set them up, and so we are not really left with that much of places, where we can put them up. Okay, so that is one reason why it is retarding the expansion of our wind projects. Comparatively, solar was relatively less. There was no, not that much, maybe about something like 8 to 10 gigawatt is what we had earlier, and that has grown by about something like 4 times. A substantial rise in solar, but nothing very significant in terms of these other things. Okay, so that's the situation as of today. They are both going hand in hand, roughly equal. Okay, now if you look at, yeah, I've shown you like the in wind. Okay, you can see we have in 14-15 we were at about 23, about 23, close to about 24 gigawatt. Okay, and we have grown to about 39 gigawatt, roughly. Okay, so you can see the kind of growth that has taken place. Okay, if I were operating it for 24 hours in a day, I would get 39 into 24 gigawatt hour. And if I were operating it at for 365 days, I would get 39 into 24 into 365. Okay, that many gigawatt hour of power I would get, and I'm actually generating 59,824. So when I divide this value by the total, theoretical, okay, this comes to about 17.6%. So our effective utilization of these installed capacity is 17.6%. Okay, this is based on the 2021 figure. I've just taken these two figures. Okay, so so this is important also to know. Okay, that it's not just about how much capacity you have set up, but actually what percentage of that compared to the theoretical you are actually generating power from. So I mean, I don't know. I mean, maybe this value is not too bad. It may not be so good, but it's also not so bad. 17.6%. I think that our solar panels, which have been set up, will also probably give you something of that sort of uh, actual electricity generation over a year, roughly. Okay. Now, there is something else which is very interesting to note over here. This is like, let's say I've taken the data for 2018, 2019, and so from April to March, so covering 12 months. Now, what you'll see is that, and it is telling you how much gigawatt hour is generated for different months. Okay. Now, you can see that from about June, uh, it suddenly shoots up. Okay. And you get June, July, August, and to some extent September. Okay. That these figures are much higher, than the figures for the rest of the month. Have you seen? Okay. These figures are relatively much less. Okay. And so what it means is that the bulk of the solar wind power in our country that we are generating is during the monsoon months. Okay. Now that is very interesting because it is in the monsoon months that my solar panels become duds, because it's so cloudy, overcast, I hardly get any power out of them. Okay. From the solar panels during those months. I mean, solar panels, you get very good power in the other months, okay? But not in those 4 months. So in a way, wind power and solar power are beautifully complementary to one another. When my solar power is low, my wind power is high. Look at this. So that's very interesting. So if you were a planner, and you say you were working for the Ministry of Renewable Energy, don't try to put all your eggs in one basket, because people who don't understand these things, okay, and they say, let's go all solar, they are missing the point that the wind is giving very good power when solar is not good. You could also think of, and in fact this is something that there's a lot of work going on everywhere, that because of the complementarity, it would also be interesting to look at. By the way, there's also a day-night complementarity, which I have not shown, that during the night times the wind generation is more, and that's when your solar power generation is less. So if you say to hell with batteries, let us just go by a combination of windmills and solar, just so that we get more or less an even distribution of power during the day, and morning and daytime and night, then that's not bad. Around a windmill, there would be a lot of empty space. Okay? And I'll tell you why you require so much of empty space. Okay? And so what will happen is that you could actually set up photovoltaic panels on the ground, okay, in those empty spaces that may not interfere at all with your wind generation. And so, I could actually have farms where I've got both solar photovoltaics and windmills, and that may be a pretty good combination, you know. So I hope you understand it is not just about the technicality of knowing about a windmill. Able to understand these kinds of effects is also very, very crucial, because this is what will make or break a project. Is this slide clear to everyone? Did everybody understand?
Yes, sir.
Okay, okay. Anyone who didn't understand, let me put it the other way around. Everyone understood? Okay, very good. Okay, now let us also look at where we stand uh, in terms of the world as a whole. Okay, so what you can see is that this is how the trend has been for uh, global wind power. Okay, in gigawatts installed capacity. Okay? So we are talking about having already reached something like 600 gigawatt, okay, globally. Okay? Now if you look at India, this figure, of course, it says 35 gigawatt, whereas here it was 38. So obviously this figure is 2018, that one was 2021. That's why there is a slight difference. Okay, but more or less it will give you similar trends. So you can see we are, in terms of installed capacity, we are at about 6% of the global installed capacity. Okay, but remember that our wind speeds are very low. Hmm? I'm just putting that so that I don't forget. Remember, however, that our wind speeds are very low. Okay, so why am I stressing this? Because now look at again China, they've become the leaders now. Okay, 36% of total installed capacity was in China. Okay, quite high. Okay, and what did we say? They have got much stronger wind speeds. Okay, so the productivity of their installed capacity will obviously be much higher than what it will be for us. No? So they installed capacity wise, they might be at say about what is about roughly about say 6 to 7 times of us. But in terms of wind generation potential, that might actually translate to something like 14, 15 times. Okay, that could be the huge difference, right? And one can go and analyze this country by country. United States, Germany is very big in wind power. You can look at United Kingdom for its size. It's quite high. All of this. Okay, and in India you can see which are the states where the maximum installed capacity exists. Okay, and these are the two bigger ones, Tamil Nadu and Gujarat. But then these states are also doing quite well: Maharashtra, Karnataka, Rajasthan, and Andhra Pradesh. Okay, and the others, it's basically peanuts. And at least now, if you didn't know all this and somebody said, hey, why don't we go and put up windmills in the eastern part? Why is it so unfair? Why should it be like this? Why can't we put up more? You could, but you'll just burn your fingers. Okay, because it will be no use. Okay? So keep this in mind, that what is the reason why these are the ones which have got maximum you know install capacity. Okay, and just so that again you can see the pockets. Okay, and this is why it's so high in Gujarat. Okay, you can see it, and also why it is so high in Tamil Nadu over here. And you can see over here that Tamil Nadu has this beautiful patch, okay, over here, where it is not in Tamil Nadu. This is actually in Kerala. Okay, but yeah, it's adjoining. I mean, that relatively it's higher. Okay, and likewise, you can see some areas here. Okay, this is, you can see lighter. So we are talking about 300 to 350 watt per square meter potential, not bad, which is the reason why more of those have been set up in these places. Okay, all right. Now, there is another thing that it's worth mentioning that and this is something of course in the next lecture again we'll cover storage issues, but what would make a lot of sense, and it would include wind power, is that during there are times when you might want to actually generate your power from the flow of water in the dam. Okay, and then what you can do is, if you have got surplus power which is getting generated, what you can do is you can continuously again start lifting this water up. Okay, and so that you will have a much higher overall generation of power, and this is an easy way to store. You see, you have already got this structure. So if I just lift the water and pump it here back, I mean, there's nothing easier than that, to exploit the potential energy. Okay, and like this, for example, has been done in the Niagara Falls. They generate much higher extra amount of electricity just by playing this kind of a game. Okay, so this is again, I would say, just like we saw the solar and the wind. I think if some of you were to in future do projects, look at our hydropower plants and look at the combination with wind, or solar, and see if we can do something clever, to make those dams overall generate more power. And this is such an easy thing to do. Just put in some pumps and just keep lifting the water whenever you've got surplus power. Just lift. Don't do anything else. Just convert it into potential energy, and all the infrastructure already exists to generate power. So I don't have to invest, really in anything. Okay, to do this. Is this clear? All understood?
Yes, sir.
Okay. Okay, now let's go into something a little more technical in terms of these windmills. Okay, and I don't want you to, go into the details of these things. Okay, you can always do that if you want to. Okay, but I just wanted to give you an understanding of the important forces, which actually operate in a wind turbine. Okay? Now there are two forces that you need to understand, and in a very simple way. Okay, one is known as lift. Okay, and the other is known as drag. Okay, now the drag force is basically a force that is generated along the direction of the wind itself. Okay, so the wind is going, let's say, in this direction. Okay, so the drag force is really generated in the same direction. Now I'm not showing you how, but the drag force also creates a rotational motion. Okay, but that's all you need to understand. The second is what is known as a lift force. Okay, and what it is these wind turbines, their blades, are of a certain design. Okay, and you can see that this area is the high pressure region and this area is the low pressure region. Okay, this area. So this part, the convex surface, is basically the low pressure region. Okay, and this is the high pressure region. Now, because of this pressure difference, it causes a lift. Okay, and the lift force is perpendicular to the wind direction. Okay, so what it does is that it leads to the rotation of the rotor, and that's how the rotors start rotating. Okay, so that's all you need to know. You don't have to go into the details of this. I mean, this is the domain of aerodynamic scientists, and there's a it's quite complex to work it out in detail. But all you need to know is the lift and the drag forces. What you also need to know, and in fact I'll show you, is that the windmills that we have in our country, which are known as the horizontal axis windmills, uh, they all their dominant mode of action is really the lift force. Okay, and of course there are other windmills which are more exploratory, not that extensively used, which is known as vertical axis windmills, and they operate more on the principle of drag. Okay, so let us now try and see, okay, just to show you that what's happening. Now the wind, so these are your rotors, they've not shown the rotor blades. Those are the ones which are rotating, okay, and this is known as the hub. Okay? This is the hub of the windmill. We will go into the details of these, okay, and the wind is blowing perpendicular to these rotors. Okay, so the rotors are turning on an axis. I mean, the rotor is rotation is perpendicular to the direction of the wind. Okay, so effectively what's happening is that this wind is creating, because of the lift force that I told you about, it creates a force which is perpendicular to the direction of the wind, and that's what makes it move, in this direction. So, and that's what causes the rotation. Okay, so it moves in this direction. Okay, and that's what causes rotation. Okay, now let's try and understand in a bit more detail. Okay, the basic equations, and it's believe me, it's quite at least at this level it is not so difficult to understand. But I will take you through it. Okay. Now remember that what is wind energy?
Sir,
What
kinetic
energy?
energy.
Absolutely, kinetic energy. Okay. Now we know what is the equation of kinetic energy. E is equal to half mv squared, right? Okay. And now what is m? M is the mass. Okay. And v is your velocity. Okay. And you've got or your wind or speed, half mv squared, is basically the kinetic energy. Okay. Now let us try and understand, okay, that suppose, like, let's say I want to calculate the total amount of energy that is present in the wind in the form of kinetic energy, okay, for a time duration of t. Okay, that's what I want to measure. Okay, so now what you have, and over what do I want to measure that? I want to measure over the entire area which is being circumscribed by these rotors, which are moving. Okay, so that's my wind is going into that area. Okay, where my rotor blades are spinning. Okay, so that is basically my area. Okay, that is that area. Okay. Now, then what else is there? Okay. Now I need to know, I have to basically get M, which is the mass, because kinetic energy is mass. So I want to find what is the total mass of air, which basically cross the wind turbines, all right, within a time t. So one is, and for that area, which is a. Okay. So what do I have now? I have my total volume. Okay, the my total volume, ABT. A is my area. This is the area of the rotor blades, the area that it is covering. Okay, V is the velocity of my wind, so it will have the unit of meter per second. Okay, and time has the unit of second. Okay, so this has the unit of meter cube. Okay? So this is the total amount of air, volume of air, which actually went past my windmill in the time t. Is that clear? A wind of velocity v going past my windmill in time t will generate, will have the unit of volume. Okay, and this is the AVT. It will be given by AVT. Okay. Now, what is uh, what else do I need to know? I need to know the density of air. Okay, and what is the density of air? Okay, you can work it out, and I was trying to do a thing. I'll show you. This is the density of air, roughly. If I have dry air, rho is equal to 1.28 kilogram per meter cube. Okay. Now, you can even actually work it out. I was just trying to work it out rather than just taking the figure from the internet. Okay. So, for example, if you look at rho, okay, I can actually work it out. So, air has what? Air has roughly one part of oxygen, O2, and four parts of nitrogen, right? Okay. So, if I want to find out, all right, that in 22.4 liters, which is 1 mole of air would occupy 22.4 liters, as you know, under normal temperature and pressure. So what would be the mass of that? It would be 1 into 32 plus 4 into 28 divided by 5, because these are the 5 parts. So I've divided by 5. Okay, so this is what I will be my total grams, okay, of air in 22.4 liters. Okay, and then I want to convert it into kilograms, so I will divide it by 1000. Okay, and then I will multiply it. Okay, because this is the figure for 22.4 liters. So whereas density is over here expressed per meter cube, which is 1000 liters. So I'll multiply by 1000 divided by 22.4. Okay, and this comes out equal to 1.285. Okay, so I have verified for myself, that yes, I mean, this density of air is a correct density. Okay, now you remember we said that in monsoon times, etc. I'm not very sure. I might be guessing a bit, but that the productivity was higher. Now, what is very interesting is that you see, when in the monsoon time, what will happen? There's so much of rain, my air is getting saturated, okay, with moisture. Okay? So it is laden with water. All right. So, that same 22.4 liters of air will now be heavier because of the presence of moisture. So, I just wanted to check. So, what I did was I went to the internet, okay, and I put uh, density of density of air at 100% relative humidity. Okay, and you can see the values are given: density of moist air. Okay, all right, and so it can go up to like at 20 degrees centigrade, roughly room temperature. It's about 1.579. Okay. So what it means is that I have got a, a heavier air, you know, moist. So I'll just put it down. Remember that moist air, it has higher density. Okay, and I'm just putting it down as what was the value? 1.579. Okay, kg per meter cube. 1 point 1.579. So we'll put it as 1.58. Okay, so it is heavier kg per meter cube at 25 degrees C, 20 degrees C, the data. Okay, so now this is very interesting. So what will happen is that your when the density goes up, obviously my total mass will go up at for constant volume. Okay, so just remember that. Now, if I this had the unit of volume AVT, okay. Now, if I multiply that by the density, and what is the unit of density? It is kg per meter cube. Okay, so AVT times density, okay, will basically have the unit of mass kg. Okay, so this can then become equal to m, this whole term, and I'll then have my half and v squared. Okay, that's what I have. Okay, so AVT rho gave me the unit of mass, and my half and v squared I have got over here. Okay, so I can also write this as total kinetic energy generated in time t equal to half rho v squared into AVT equal to kinetic energy per unit volume into total volume of air flowing in time t. Okay, and so this is what it is. Now, what is very interesting is that this term AVT also has V in it, right? So if I club this V with this V squared, which is from that half mv squared, okay, it becomes, this equation becomes half AT rho V cube. Okay, and if I divide my energy by time, what will I get? I'll get power. This is the total joules, and joules per time will be watt. Okay, so energy divided by time. So my unit of watt, a unit of power will be basically half a rho v cube. A rho v cube, just have divided by time. Okay, and if I want to know the total energy, I'll keep it as half at rho v cube. Okay, now what do you see? You see, what you see now is that the power, this is that, that power density of wind, which we were seeing here, wind power density, okay, watt per meter squared. Now, this wind power density, therefore, basically is proportional to the cube of the wind velocity. All right. So if my wind velocity increases by a factor of 2, my power increases by a factor of 8. That's how critical wind velocity is. Okay. So if somebody sees, some place it is 4 and another place is 5, 4 cube is 64. 5 cube is 125. It's twice. Just a variation from 4 meter per second to 5 meter per second. I would have increased my power density by 2 times. This is at the heart of wind power. Remember that, let's put it down that power density in air, okay, varies as the cube of wind velocity and linearly with density of air. Okay, so now this is the velocity term, and now, as I said, if for example, if I have got a heavier air, so naturally that will affect my mass, because I'm multiplying it over here. So I'll be multiplying with a higher value of density, so my total mass of air will naturally increase, and so both of these will lead to an increase in the amount of power that I will get out. Okay. Now there is one more. These are the very basic things about wind energy. Okay, but we'll keep it simple. You don't have to worry about too much of this equation. I just want you to know some basic things. Okay. Now, so let's say, what are we doing? We are actually, this is my wind, right, which is going, and it is going perpendicular to, let's say, these rotors, okay, these things. Okay, so let's say this is my initial velocity. Okay, now it will increase a bit here. Don't worry about why it increases. It increases for a reason, and after it has done its job and it is passed, then what will happen is that that same airstream will cover a much larger area, A2. Okay, so it starts with an area A1. At the time that it is interacting with the wind, the area is A. With the windmill, the area is A, and at the time that it is passed, it will basically spread over this larger area over here. Why is that? The reason is because, you see, I mean, what did my wind do? My wind actually interacted with this turbine and dissipated some of its energy. Okay, and therefore its velocity will reduce when it passes through the wind turbine and comes on the backside of the wind turbine. Okay, now the velocity will reduce, but now what will happen is that I still have to reckon with this amount of mass. This is my mass of air. I have to have continuity of mass. Okay, of I have to conserve mass. So the only way I can conserve mass is that mass is really distributed now over a larger area. Okay, so that when it is passing, okay, because the velocity has gone down, so only then will the mass over here and the mass over here become equal. All right. So effectively, that's what happens in terms of the path that the wind takes. Now, I'm not going to go through this whole thing. Okay. So this is your V1, this is your V2, and what the wind turbine will feel is really the average of this V1 and this V2. So over here, the effective wind velocity will be basically V1 plus V2 divided by 2. That's what the wind velocity here will be. Okay. Now, what you need to understand is that all of the wind which is flowing through this wind turbine is not being used by the rotor. The reason for that is that it has got a residual velocity here. Okay, so it did not really, otherwise the velocity would have become zero if all of this had basically dissipated at the windmill, which never happens. Okay, so the coefficient of performance, okay, is basically what it is that what was the power, effective power density, which was taken up by this wind turbine. Okay? That will be equal to the initial power density which I had, P1, minus the residual power density after it has gone through the windmill. So it will be P1 minus P2, and that will be P effective. And so what is the fraction which I used? It will be CP. Some people also write it as COP, okay, which is the coefficient of performance, okay, and that will be equal to P effective, the actual amount of power which was transmitted to the rotor divided by the initial power which was present in my wind. Okay. Now, I'm not going to go through this equation, but it can be written in this particular form, right? Cp is equal to 1 plus x into 1 minus x squared divided by 2, okay? And, this x is nothing but the ratio of V2 over V1, okay? V2 over V1, the wind velocity here and the wind velocity here, okay? That's basically what x is. Okay. So now what they've done is a very smart thing. By analyzing this equation, what they said is, so what would be the maximum amount of this value of the coefficient of performance, which is the fraction of the power which is utilized, how much can it be? Okay. So what they did is that they, I can expand this equation, okay, and then I differentiate with respect to x, and I equate it to 0, because that will be my maxima. This is that numerator when I have expanded it. So what am I now doing? I'm basically putting dCp dx okay is, and I have to do dCp dP or Cx of this. This term will become minus 3x squared, okay, and this term will become 1, and this term will become minus
minus
2x.
2x.
Okay, so I can equivalently write it as 3x squared plus 2x minus 1 equal to 0. Okay, 3x squared plus 2x minus 1, and I'm putting it equal to 0. Okay, and then I basically have to solve for this particular equation. Please just solve it at at home, okay, and show for yourself that x is equal to 1/3, okay, when you solve this, right? And so what will happen is, now I know that x is equal to basically v2 upon v1, okay, so I can substitute, okay, that value. So I've got v2 upon v1 will be equal to 1/3, okay, so I can put in the value of x over here, all right, and what you will find is that the maxima of cp will be equal to will come out equal to 0.59. Yeah, it comes to 0.593. Okay, you can just do it for yourself. Huh? Just put in this value of x, 1/3. Okay, first you solve this. Get the value of x. X will be 1/3. Okay, and then you put in this value of x over here, and you'll get a value of 0.59 for CP. Okay, and so what that means is that this is the theoretical limit. You know, you cannot convert more than 59% of the total amount of power that is available in your wind. Not more than 59% can be converted into rotational motion. Okay, so that's very important, and this is known as the Betz limit, BETZ. Okay, Betz limit. Okay, so and in fact, this is only a theoretical value. The actual values are much less. It will be somewhere of the order of 30 to 35%. You know, 0.3 to 0.35. So again, you know, it is not very different from thermal energy being converted into power. You know, typically, you know, the efficiency will be about 30%. Okay, so here again, the practical efficiency of converting wind power into the rotational motion, that's not the entire thing, into the rotational motion, will come to roughly about 0.3 to 0.35. Okay, now another thing that you need to note over here is that, and I'll read it out, another wind turbine located too close behind would be driven only by slower air. So if you think that you'll put more of these, another one wind turbine quite close to this, it won't work. Okay, because this will be at a much lower wind velocity. Okay, so what you need to do is that they worked it out that therefore wind farms in the prevailing wind direction need a minimum distance of 8 times the rotor diameter. Okay, so suppose I've got a rotor diameter of say 100 meter, no, then between the two windmills I have to have 800 meters gap, all right, to make sure that none of the effect of this is felt on the next windmill, you know, and the next windmill is seeing fresh air, okay, with a velocity of v1. All right, so and the usual diameter of wind turbines is 50 meter with an installed capacity of 1 megawatt, and 126 meter with a 5 megawatt wind turbine. Okay, so I mean that's all you need to know. So remember that there is a criticality, okay, in terms of also the spacing of the windmills. All right, now let us look at, you know, the construction of the windmill. Okay, it is let's look at all the terms over here, and we will go one by one. Okay, one is basically your foundation. Okay? This is your foundation. Two is the connection to the electrical grid. So you finally, what are you doing? You're generating power, you know, and then this power is normally connected to the grid. Okay, so this is basically to make the connection to the grid. Two. Three is your actual tower. And we have seen the criticality of the wind speed, and at different heights, the wind velocity is different. So you have to make your tower of that kind of a height. And in that tower, you'll have to put either an elevator or you'll have to put ladders, so that people can actually climb up and repair things. If things go bad, I mean, and it's not easy to do this because we are talking about such a height. Okay, so inside this there will be ladders. Okay, then what you have is an access ladder. Okay, so that is the access ladder. Okay, then you have a wind orientation control. Okay, so what it is that wind direction is changing. Okay? And just like you remember, we were tracking the sun. Okay, you can have these XY trackers. Similarly, you need to track the wind and just make sure that your wind turbines are perpendicular to the direction of the wind. Okay, and that is done by what is known as a wind orientation control, the yaw control. Okay, that is the yaw control. So you can see it can basically pivot around this tower. It can rotate. So sometimes you'll find the windmills, it was facing in one direction, then it's in another direction. Okay, the sixth is what is known as the nacelle. That is the main housing. You from the outside you cannot see all these inside stuff. What is there? Okay, so the nacelle is basically the housing for this unit. Okay, seven is the generator. What is happening is that when these things are rotating, okay, it is basically by Faraday's laws, it is undergoing an electromagnetic induction and it is generating power. Okay, so that is the generator. Okay, 7 is the generator. 8 is a wind sensor, anemometer. Okay, so this actually senses both the intensity of the wind as well as the direction of the wind. Okay, so effectively that's what you are doing with this. Okay, and then there are some electric or mechanical brakes, which you need to put. Like sometimes, if for example the wind power is excessive and the windmill is going out of control, I need to brake it. So I need to have some brakes. Okay, then I have a gearbox. What the gearbox does is that it converts the initial rotation of this, okay, which is basically defined by a very low speed rotation with a high torque, and the gearbox converts it into a high speed rotation with a low torque, which is what you require to generate electrical power. Okay, and otherwise you cannot do it with such a low rotation. Okay, so that I have a gearbox for that, and these are my rotor blades. These are the blades. Okay, and 12 is not only are these blades, they are not fixed. They can actually be twisted a bit. They can, so that that pitch and lift and all that stuff that I mentioned to you about, you can optimize these by varying the pitch of the blade. Okay, and this is the rotor hub. So this is the hub, and so these blades are basically connected to this hub. Okay, the yaw control, okay, is basically, as I said, is the angle of rotation of the nacelle around its vertical axis. So that's effectively what you have. Okay, and the pitch control is really what gives you the optimum best angle, of the blades with respect to the wind. Okay, so that's the effective construction of the windmill. Okay, so in details, this is what it looks like. Okay, so these are my rotors going round. Okay, these ones. Okay, and it is moving this horizontal axle. Okay, this is what is rotating. Now this is connected to a gearbox, and so initially when this is rotating, this gearbox is connected to this, and effectively it is it is being converted into a very high speed rotation, from this. Okay. And this is the generator. This is where you have your magnet, and you know that when I've got a rotating coil, okay, and in a magnetic field, that it will generate electricity. Okay. That's basically how you generate electricity. Now, for those who may be interested, okay, what happens is that this rotation, is effectively, this is the rotation of the turbine blades because of the wind. Okay. And then when these blades are rotating, okay, what it is doing is that it is exerting a force on this horizontal axle. Okay. And that is basically controlled, okay, by the torque is equal to the r, that is the distance at which you are exerting this force. This is that r. Okay. And the force that you are applying, that green, okay, that is basically the amount of force that you're applying. Okay. So it's a cross product, r cross f, and tau is basically expressed as rf sine theta as a cross product. Okay. Torque is effectively a force, and when you multiply it by the angular displacement, you will be able to calculate the total amount of energy that you're actually getting. That's effectively this. Don't worry about it. Don't even worry about this. I just thought I'll show you that how exactly the torque, is basically being used, to move this axle around. Okay. Now, there's also, this is what is known as the horizontal axis windmill. Why? Because this is horizontal to this tower. This is horizontal. Okay. And that's why you needed such a long, high ladder to climb up and fix these things. Okay. But there is also something known as a vertical axle windmill. It looks something like this. We don't have these. I haven't seen these in our country, but it's more of still a pilot thing, not really something that has become very popular. But there are certain advantages of the vertical axle windmill, that mainly that these things, the generator, the gearbox, etc., you can actually locate over here. So now you see the rotation is over here. Okay. So whereas here it is rotating around this. Okay. So you can set up your generators, etc., close to the ground, so it's much easier to maintain. Okay. This one operates more on the principle of drag. Don't go into it. Just remember this, that it operates more on the principle of drag, whereas this one operates more on the principle of lift. Okay. The horizontal axis thing. Now, there is one more very critical thing that one needs to calculate, okay, by way of designing a windmill, and that is to know that what should be the length of the blades, the rotor blades. Okay. Now, what it is that these blades, which are spinning, okay, the blade spin at the tip of the blade is what is known as the tip speed. At the tip of the blade, whatever is the speed at which the blade is rotating. Okay. And you have the actual velocity of the wind. Okay. So that ratio of the blade speed, and it is the tangential speed. So when it is rotating, if it goes off at a tangent, at what speed will that go off? That is basically the tangential speed. Okay. So the tangential speed divided by the wind velocity, all right, is known as a tip speed ratio. Okay. And typically there is these are things you don't need to worry about, but there has been a very detailed calculation which has been done, which shows that optimum performance you can get when this ratio, the tip speed ratio, is something around 6. You can see a value of 6. Okay, so this is the tip speed velocity, this is the wind velocity, the ratio is just a number. Okay, and so now what they're doing is, suppose, let's say I am having a wind speed of 15 meter per second. Okay, now my tip speed velocity now from this equation will be equal to 6 into 15, which will be equal to 90 meter per second. Okay, now this tip speed velocity, okay, is what it is basically the again, don't worry about this. Okay, this is the angular velocity multiplied by the radius. That is the conversion between the tip speed velocity and the angular velocity. Okay, and the angular velocity is basically one rotation is equal to 2 pi, as you know, 2 pi radians. And suppose I've got n rotations. Okay, then my total angular velocity will be equal to 2 pi n. All right, now if I've got n rotations per minute, and if I have to express it per second, okay, because my power etc are calculated in seconds, so I'll divide by 60. So 2 pi n divided by 60, all right, is basically my angular velocity expressed in second. All right, okay, now this omega r means what? This is omega 2 pi n upon 60 multiplied by r. R is what? R is the radius of my blade. Okay, this one. Okay, and so r is equal to VTS, okay, which is equal to 90. And from that I can get, if I divide 90 by 2 pi, all right, multiply 90 by 60 and divide by 2 pi, you will come to a value of 860. Okay, now 90 into 60 divided by 2 pi. Okay, that will give you a value of 860. Now if I have got this and my blade, suppose I've designed it in a way that it is sweeping once every second, which means that it has to have 60 rotations per minute, RPM, 60 RPM. So my value, of n is equal to 60. Okay, 60 rotations per minute is equal to 1 rotation per second. And for power, I need to do calculations in second. Okay, so I can write this as R into 60 is equal to 860. And from that, I'll get a value of R, which is equal to 14.33 meter. Okay, so this is basically the radius of my rotor blade. The length of my blade. Okay, now if I have this calculation is for if I've got only a one blade. Suppose I've got a windmill with only one blade. Now suppose instead of that I have a windmill with 3 blades. Okay? So what will happen is that now my n will be equal to 20. Why? Because I've got 3 blades to basically cover 1 round per second. So nr will now become equal to 20r. Okay, so 20r is equal to 860, and from there r will be equal to, I can calculate, it will be equal to 43 meter. So depending on how many blades you are using, whether it's 1 blade or 2 blades or 3 blades or 4 blades, I will optimize the length of my blade. Okay, and it will also depend on this tip speed ratio. And typically, as I told you, they take a tip speed ratio of 6. Once I've got my R, from that I know my A, because A is what? Is just equal to pi r squared. Okay, so pi into 14.33 whole squared. Okay, 14.33 meter. I'm doing it for this one. Okay, so I get this is my A, and then my power is equal to half A rho V cube. You put in the value of rho and put in the wind speed. Like for example, here the wind speed was taken as 15 meter per second or whatever it is, 8 meter per second. You put that wind speed in, and from that you will get the total theoretical power. Okay, this total theoretical power is basically what we are talking about, is effectively the power in the wind as it is passing through my rotors. Okay, that power, okay, and then of course the fraction of that power which is being used to finally generate electricity will be this. P is equal to 0.5, that is coming from my half, okay, pi r squared, this is that term, pi, your rotor blade is r, okay, and your, let's say, the air density, suppose in this particular equation, they have taken air density at 1.225. That's fine. It's a data, kg per meter cube. So I'm putting that value in, okay, and my wind speed they have taken as let's say 4.5 meter per second, okay, in this particular calculation. Okay, now this is that coefficient of performance which we talked about, which theoretically is 0.59, that is the maximum that it can be, but normally the COP is of the order of 0.3 to 0.35, not more than that. Then there are other losses, like for example, ng, is basically when what is the efficiency with which, my electricity is finally being generated, by the generator. Okay. Now, typically the efficiency is about 80%. So I can put in 0.8. Okay. And there is also a gearbox efficiency, okay, which is that it is connected to this gearbox, okay, this rotor, and this is connected to this gearbox, so that I am converting high torque low rpm into low torque high rpm, okay, and there is a little loss over there also, and this ratio is about, or this efficiency is about 95%. So I can put in all those values, okay. Power is equal to 0.5 pi, rho is equal to, I'll put 1.225, okay, v is equal to 4.5 meter per second, coefficient of performance I've taken at 0.35, okay, ng, the gearbox efficiency I've taken at 0.95, and the generator efficiency I've taken at 0.8, okay, and effectively you can from that you can calculate that for a given windmill with a particular radius, with a particular coefficient of performance, with a particular wind velocity which is seeing, that effectively how much power I will generate in terms of joules of electrical power, you per second. What is what I'll basically calculate. Okay. If you recall the work that was done with oxen-powered RO, perhaps you can do a direct connecting of the rotor shaft of the windmill to the pump of the seawater RO, and that would be very interesting because that way you can bypass the electric generator, and maybe you can increase the overall efficiency of the process and also reduce cost. This is a scheme that was developed along with the Sardar Patel Institute in Mumbai, and I just thought I will show it to you, that there is possible scope for innovation in some of this. It's best that I not load you with any more of information, okay, around windmill, okay, but I think that you would have understood the essence of how a windmill operates. Don't worry about all the mathematical derivations of this. Maybe the important derivation of that power density depends on the cube of the wind velocity. These things are of course important because they are at the heart of the whole process, and you'll be able to work it out. It's not very complicated. Have you roughly got an idea of what it is?
Yes, sir.
Aishwarya, are you clear? Did you understand?
Yes, sir.
Okay.